Hello guys and gals, and welcome to my second video on free response questions and review. Um, Today we're going to look at the dreaded polar question. Ooh. And I know that wasn't fun during the year, so we'll try to do our best with it. And you'll also see that in this particular question we're going to look at today, they actually involve limits as well. So a little joke here to ease the burden and the pain. Before we actually look at the question itself, I wanted to just show you guys the mean scores for the different free response questions on the 2019 exam. Yesterday, my prior video was question number 1. The average there out of 9 was a little more than 5, and that was actually the best average score on all the free response questions from last year's exam. And I want you guys to be aware that these mean scores are somewhat typical from year to year. So you're not necessarily expected to get perfect scores on these. You just want to try and do your best job on it. And you can see here, we're going to look at question number 2, which was the polar question. And unfortunately, that was the lowest mean score out of all the questions. So you're not alone. No one really enjoys polar questions, and this one was a bit difficult from last year. So without any further ado, let's actually look at last year's polar question. So you see here in this problem, we have the picture of our polar curve. They tell you that let S be the region bounded by the graph of the polar curve r theta, and they give you the equation. This is on the interval from 0 to square root pi, and again, we see the picture up above. I will say that this is a calculator-based problem, so you probably would have wanted to punch this into your equation to graph in polar mode. And remember, you can limit exactly the range of angles that your calculator actually graphs this from, because if you don't, you'll see a crazy graph. You only want to graph this from 0 to square root pi. So with that given information, as well as the picture of our curve, you'll see that there were actually 4 parts to this particular problem. Let's start off with part A. Part A asks you to find the area of this region S. If you recall from our work during the year, the area of any region within a polar curve was the definite integral from the angle A to the angle B. Those two angles rotate you through the particular region. And then the integrand was 1/2 r squared d theta, where r represented typically your polar function. So in this particular problem, again, it's a calculator-based problem, and if you already graphed this on your calculator, you would have noted that from 0 to square root pi, that actually revolves you straight through this particular region. So the angles 0 and square root pi are the angles that we want to use for our definite integral to capture the area of our region. So we can write that the area equals the definite integral starting at the angle of 0 up to the angle of square root pi. Our integrand would be 1/2, and our function r is this function here. And now remember that since they have defined for us what r theta is, it's this equation, we can use that variable expression in our answer. And then I'll just write d theta here. And this definite integral will capture the area of this region. And again, this is a calculator-based problem, so we can evaluate this on our calculator. And the value of this definite integral is 3.534 to 3 decimal places. So that would be our answer for part A. So now let's move on to part B. Part B asks us, what is the average distance from the origin to a point on the polar curve, given our polar curve r, on the interval from 0 to square root pi? So now, if you recall, with our work with polar curves, the angle theta is the angle that we are at when we rotate around a particular curve, and r represents the distance from the origin out to any particular point on our curve when we rotate that angle theta. And so if you also recall from my video from yesterday and yesterday's problem, the average value of any function f of x on an interval from a to b is equal to 1 over b minus a definite integral from a to b of f of x dx. And so since that's the generic formula that we use to find the average value of any function, to find the average distance of any point in the curve from the origin to that point, we can find that average distance by setting that equal to 1 over the difference of the values of our interval, which in our case is going from 0 to square root pi. So I'll write 1 over square root pi minus 0 times the definite integral. Limits of integration also will go from 0 to square root pi, because that's the endpoints of our interval. And our function here is our function r theta, because remember again, r tells us the distance from the origin out to any point in our curve. And this is the setup of our expression that will calculate that average distance. And once again, we can evaluate this on our calculator and round it to 3 decimal places. We get 1.580. And voila, we have the answer to part B. All right, now on to part C, where things get interesting. In part C, they say there's a line through the origin with positive slope m that divides the region S into 2 regions with equal areas. So they want us to write, but do not solve, an equation involving one or more integrals whose solution gives the value of m. The first thing I'm going to do is I'm going to do my best to draw a line through the origin that splits the region S into 2 equal parts. So let's say that's that line. And now this line has positive slope m, and because of that, we can write an equation to this line. Again, it's going through the origin, slope of m. So the equation of this line should equal y equals to mx. Now, this line again is supposed to be dividing the region S into 2 equal areas. To find, say, the area of this side of the region, we could set up a definite integral like we did in part A. The integrand would be r theta, and the angles, the lower limit should be 0, and as we rotate around, when we get up to this point here, that angle there, which I'll call theta, would be the upper limit integration to give us the area of this region here, which should be half of S. So if we can solve for what this angle theta is, we'd be golden, we would have our answer. I'm going to redraw what we have here, but I'm just going to draw the line y equals to mx, and this is our xy coordinate plane. And I'm going to look at this line in a little bit more detail, because if we look at any point in this line, well, let's go to this point here, it's going to have coordinates x comma y. And if we drop a perpendicular from that point of the line to the x-axis, we form our right triangle. And the reason why I'm doing this is that, remember, trigonometry has its foundations from right triangles. And in this right triangle, well, right over here at the origin, well, that's our angle theta, which we're looking for. The legs of this right triangle, well, this leg here we can denote by the variable y, which is the y coordinate at this point. And this leg of a right triangle we can denote by x. It should be the x coordinate at this particular point right here. And working off of our knowledge of special right triangles, we know that the tangent of our angle theta should equal the opposite side from the angle theta, which is y, over the adjacent side of x. And while this is definitely true for this right triangle, if we look even more closely at our equation for this line, if we were to say solve for m, note that if we did solve for m, m would equal y over x. And so now we have this connection that the tangent of theta should equal m, And if we want to solve for this angle theta, well, then we can do that by essentially taking the arctan of both sides of this equation, and we would have that the tangent, oops, didn't want theta there, wanted m, that theta should equal the arctan of m. And now that we know the value of this angle theta, we can write our equation that we could use to ultimately solve for the value of m. So in this equation, we'll write the area of this half region, which should start at the angle 0, should go up to this angle of theta, which is being represented by the arctan of m. Our integrand would be 1/2 of r of theta, the equation of our graph, d theta. And now this should give us the area of this region here, which is 1/2 the area of the entire region. So it should be equal to 1/2 the area of our entire region, which, if you recall from part A, was 1/2 of the definite integral from 0 to square root pi of 1/2 r of theta, whole thing squared, d theta. And although it's a bit painful, this entire equation could be used ultimately to solve for the variable m as described in the problem, because there's the variable m and we have our equation. This could be used to solve for that. We don't have to, we just need to come up with that equation. Whew. So now let's go to part D. Part D, more interesting stuff here, said for k greater than 0, let a of k be the area of the portion of the region S that we have here that is also inside the circle r equals to k cosine theta. And here comes our limit. They want us to find this limit, the limit of a of k as k approaches infinity. Now, to get some sense out of this, it would make sense perhaps to look at the graph of not only our curve r of theta that we start off in the beginning of the problem, but also the graph of this particular circle and see how what's happened here. So you could have brought this up onto your calculator. I'm going to bring this up on Desmos. And so you see the graph of our original polar curve, and here is the graph of our circle with k. K right now has a value of 1. Now, on your calculator, you could perhaps, change the value of k. You can look at what happens to this circle as k gets larger. And I'm going to play this animation to see that as k is getting larger, the circle obviously is getting bigger. And if you notice the shared region between that circle and the graph of our polar curve, it's basically becoming almost this entire region here of S. Now, if I could bring this and show you. So here's our circle getting bigger and bigger and bigger. And essentially notice that the circle is staying on the right side of the y-axis. And it's as if this circle is going to continue to get bigger and bigger and bigger. It's never going to cross over the y-axis. It's just going to get bigger and bigger and bigger. This part of our circle is almost going to continue to get closer and closer to the y-axis. So the region, the area that's combined between the circle and our original graph is basically going to be the region inside of S that is in the first quadrant. That would stop at this point here on our polar curve. So if we were going to get the value of this limit here, I claim it's basically going to be the area that's inside our polar curve, starting at 0, but stopping when we get to this point right here on our polar curve. And since that point is on the y-axis, it would stand to reason that would be at the angle of pi over 2, because that's 90 degrees. That's when we get to when we stop at this point in the y-axis. And if you want to check to make sure that at pi over 2 we're at this point of polar curve, remember you can limit your calculator and how far it graphs your polar curve, you can set the upper limit to be pi over 2, and notice that we get this part of our polar curve just in the first quadrant. So the limit of a of k as k approaches infinity is essentially going to equal the definite integral from 0 to pi over 2 of 1/2 r of theta, whole thing squared d theta. And the value of that definite integral is 3.324. So that was definitely a very challenging problem. There definitely are some difficult parts to this question. Parts A and B, I think, were a little bit easier. Parts C and D definitely were very challenging and a bit difficult, rather unusual parts to a typical polar problem. If you want to look at some other polar free response questions, 2017 number 2 is another polar problem, and then also 2014 number 2 was another polar free response question. So you can look at those. There definitely are parts of those problems that are easier than others, and as with the case of this problem here, sometimes they get a little bit challenging. But I hope that this video was helpful to you guys understanding this polar question. As always, if you have any questions at all, you can let me know over Google Classroom. And I hope that everything is going well with you guys and that you stay safe and take care of yourselves. I'll talk to you soon.